Hello, we're back considering the nature of energy and building on our previous discussion on what is energy and trying to look more specifically at the nature of work and heat, two key ideas that are central to our understanding of energy and the science of thermodynamics. In the previous video, we started off with some fairly hand waving definition of energy just to get started. We defined it as something that is the subject of changing things, so very general and a bit vague. And then we tried to look at some of the more specific examples of energy, and we went through thermal, mechanical, electrical, chemical, and nuclear. These five famous forms of energy. And I made the claim that these five forms of energy are all described by a common connecting series of principles. Quite a quite a claim if you think about it. And then we talked a bit about the distinction between classical thermodynamics and statistical thermodynamics. Just a very brief discussion about that. Well, as I said, we're today going to talk a lot more about some of the details of what we mean by the terms work and heat. All right. And so this is now getting to the heart of the formation of classical thermodynamics. These are the issues that were at the heart of debates and detailed analysis in the 19th century, with all sorts of famous figures involved, like Lord Kelvin, like Joule, whose work we're about to discuss in some detail, and also German theorists like Clausius and other brilliant people. So this was a great subject of debate, coming to grips with what these things were and how are they related. So I think we should start off by just looking at the issues. So let's start with the concept of work. All right. So work. Now, work is sort of an everyday term. We kind of understand what work is. And when you start trying to stop and think about what you mean by work, it starts getting a little bit harder to define. And there were a number of loose definitions of work before the 19th century, but during the 19th century, major thinkers started to really try to categorize what we mean by work. And when you start thinking about work, you realize it's at its most fundamental level, particularly mechanical work. Let's start with mechanical work. Mechanical work is about having to use a force to move an object some distance. All right. So if I've got my coffee cup here again. So if I get my coffee cup and I move it across the desk I'm sitting here at the moment, I'm pushing that cup against the surface of the desk, and what's resisting its flow is friction. And it takes work to overcome that friction, right? I have to apply a force, and I am exerting work. I am carrying out work, would be a better way of putting it. And that will be a function of also how far I move it, right? So we start seeing there are two critical elements in that simple idea of mechanical work, which is there's a force, right? There's some force being applied, and there is some distance involved. All right. So that idea started to take shape in the 19th century, and people started to see that that was a useful way of thinking about work. Um, I think one of the most particular examples of work that is probably very relevant to when we talk about James Joule's famous experiments, and they really are very, very famous experiments about the nature of work. Um, we can either think about an object that is either going up, being pushed up, or pushed down. So in this system here, when I get this cup and I move that upwards, I'm definitely exerting a force. What I'm doing is I'm exerting a force to overcome the effect of gravity. All right. So certainly by the early 19th century, and we understand well now that if I move that cup, I'm pushing against gravity. Gravity's trying to pull this down. And we actually have fairly precise ways of measuring what that force is, because we know, for example, that the acceleration on the face of the Earth due to gravity is 9.81 meters per second per second. Right? That's the force. Well, the force is defined in terms of mass times acceleration, for those who remember some high school physics. But if this was 1 kilo cup, for example, then and I'm trying to push this up, I'm trying to overcome 1 times 9.81 kilograms per meters per second, and we call that force, and we give that the units Newton, the name of the person who identified that. So I've got to overcome that force. But now, by going from a certain distance, I'm doing work. So in this situation, we define work as that force multiplied by the distance. So in this case, if I go up like 100 millimeters, it's 0.1 of a meter. All right. Or if I'm in imperial units, 1 foot. If I go a little bit further, it's more than 100 millimeters a foot, of course. So we start seeing that we get the notion that work in this scenario is the force being applied to lift that object that distance. So basically force by distance. So, all right. So this is, now I should explain to you, I'm simplifying the problem slightly, because as I do my work, push this up, I'm also overcoming the friction of the air. So we're going to ignore that, just to make the calculations easy. I should say that would be quite trivial compared to the force required to move the cup. So just the weight of it. So we basically have this simple definition of work that, force times the distance. All right. So if you start accepting that as a reasonable definition for mechanical work, then it can make us start thinking of some thought experiments, because we're going, well, we're doing that work. Does that relate to any other types of energy, or can I turn that work into other forms of energy? All right. This is the kind of thought experiment that James Joule was thinking about. And I should tell you a little bit about James Joule. James Joule was born in the north of England. He was the son of a wealthy brewer. He spent most of his life working as a brewer. So he was a brewer principally in his occupation, but his hobby or his enthusiasm was for physics and mathematics. And he made some very wonderful contributions, actually, to those fields. The one we're talking about is probably the most famous, which is trying to understand the nature of work and energy, which I'm just about to describe to you in a minute. And the other thing that a couple of things he did that was really fantastic, is he also showed the same relationships between electrical energy and work. So he was studying the comparison of electrical energy as well, which we're not going to talk about today, but well worthy of some discussion. And another thing he did that was really quite brilliant is he identified that when gases rapidly expand, they cause cooling. And that effect is named in honor of him, called the Joule-Thomson effect. So it's named after two people, and is central to refrigeration. So this gentleman made a incredible contribution to many important aspects of of the science of energy, thermodynamics, and practically to humanity. Imagine the value of refrigeration. Anyway, that's another topic. At the moment, we're talking about his famous experiments from the 1840s about the nature of work and heat. All right. So, Joule, being a gentleman science, but also a wealthy gentleman science, he had access to lots of equipment, being in charge of a brewery, and he was able to do very accurate experiments, even by the standards of today, very accurate experiments. I know that he is measuring temperature to the accuracy of, I think, 1/200th of a degree of Fahrenheit, which is actually, even by today's standards, a very accurate measurement of temperature. And he also very accurately, he carried out many experiments to show their repeatability. And so his papers are actually very easy to read. They can be accessed on the internet quite readily. And you're reading a person that is being very careful, very accurate checking everything before he makes a claim. So it's really good, rigorous science. And what's everything really inspiring about Jules is that he doesn't come with a PhD from Cambridge or any such thing. He's a person doing experiments in a basically a sort of an industrial laboratory, and he did these experiments and was said with great care. So there's a lot to admire, and I think one thing we should all remind ourselves: so many brilliant breakthroughs in science are not carried out by professors at universities or people in big government laboratories or industrial laboratories. They're carried out by people doing literally experiments in their garage at that level. And Joule is, I'm sure, the hero of all those people. Anyway, what he was grappling with was, well, work should be related to heat somehow. Can I construct an experiment to demonstrate that? Now, I should say at that time, it was pretty well understood in a qualitative way that if you applied some friction to a material, a solid's the easiest one. If you rub a solid, it'll get warmer, right? So you put some mechanical work into a solid, you'll make it hotter. People knew that quite well. Not sure of the relationship. And people also knew that fluids had some resistance to flow, which we call viscosity. So if you stir a fluid, there is a friction to the flow going on. Now, you've got to remember, at this stage, we didn't really have a real picture of molecules or what was happening. We now understand that that friction is all about the interactions of molecules, right? We understand that when you stir a liquid, you are basically making molecules move quicker, and you are causing interaction between those molecules. And this is part of why they get warmer. And we also understand now quite well that everything that a liquid, solid, gas, if you make it hotter, the molecules move around quicker. So we started to understand that, well, we know now that heat is all about the excitement of these molecules in solid, liquid, gas form, but it also about there that that movement is also related to the temperature. So there's this relationship between the exciting movement of molecules and temperature. This was not clear at that stage. People were still trying to make sense of those things. So, but he deduced, well, if I get a known amount of work put into a system, like stirring a liquid, and if I very accurately measure the temperature rise caused by that work, then I can show the equivalence between heat and work. See the thinking? So he constructed this experiment, and this experiment basically was a solid lump of material falling down and unwinding an impeller that was stirred in a bottle of water. And this bottle was very, very well insulated, so you didn't lose any heat, very small amounts of heat. And he also made sure that the whole system of unwinding the mechanical system had very low friction. And he also very carefully quantified how much friction was involved. So these are really careful experiments, right? Which he documents in these papers, which you can read on the internet at your leisure. And he did these experiments, and he showed absolutely comprehensively that there was a predictable amount of conversion from a certain amount of work into a certain amount of heat, depending on whatever fluid that you used, and that there was the same quantity of heat transferred for a given height of that solid falling down a certain distance. And he really did show a really fundamental, incredibly important point, is that work and heat are both forms of energy, and they can be interchanged with each other. So this was a brilliant set of experiments and also a profound insight. And he speculated, because he didn't know, but he speculated that what was actually occurring as you stirred the fluid with this little impeller that's been stirred by this contraption that he'd constructed, that you were actually seeing molecules moving faster and resulting in greater collision between the molecules. And he speculated that this was what was, in fact, the nature of the temperature rise. I suppose another brilliant insight that is coming from these experiments is, of course, that heat flows from high temperature. Temperature is a movement, and that that heat transfers along a gradient from hot to cold. So that's not explicitly what he's trying to do in these experiments, but that kind of thinking is emerging from these kind of experiments, right? But first of all, the most important realization is that the amount of energy from a solid forming a known height to perform work could be transferred to a very known and repeatable piece of energy, regardless of what fluid you happen to be stirring. I think he tried mercury and he tried water, and he may have tried some other fluids as well. So he did these very careful measurements and showed that it was the same lump of energy over and over again. And that is something that's really impressive about thermodynamics, is this realization that there are energy that comes in discrete amounts depending on the defined conditions of the system. All right. So if you can define the end point and start point of a system, you can define the limits of how much energy can be generated or converted or transferred, whatever you're studying. And Joule's experiments are a great step along that type of thinking. So these were extraordinary experiments. This experiment, just for those who know, was first published in 1845. It was read in Cambridge at a meeting of the British Association, and it caused an immediate giant debate across a world for everybody who was thinking about this. And it only took a few years to basically everybody who was thinking about this carefully came to the conclusion that his experiments were a profound insight, and basically worked very much towards establishing of a really rigorous statement of what we now call the first law of thermodynamics, which will be the subject of a future video. So, but the first thing is to appreciate the elegance of what Joule did. And if you go look on the internet, you'll find numerous videos showing people reconstructing this experiment and people describing the details of it. You can read Joule's paper, and I encourage you to, because it really gives you a sense of what a rigorous and very impressive experimentalist was James Joule. So we've reached this point now where we can say with some confidence that work and heat are different forms of energy. There are repeatable methods of transferring energy that can be demonstrated, and are quite amazing. I want to mention a special little feature about Joule's experiment, which is not the purpose of Joule's experiment, but it's actually leading on to another extremely important point, is that when he transferred this energy from a solid forming from a known distance, it wasn't a perfect transfer of work into heat. That there was always, even however careful he was and how much trouble he took, always a little bit of loss in the system. This in itself is another extremely important aspect about understanding the nature of energy, in that this transfer of energy, that there are things that you cannot avoid being lost. And this is itself a source of another very important principle in thermodynamics about what we call about irreversibilities, which we will talk about in the future. But just something to have you think about, that it isn't really possible to get a perfect transfer of energy from from the solid form down making work to the stirring of the liquid. It by its nature cannot be perfect. That in itself is another important realization, which we will talk further about. Anyway, I hope I've got you thinking about the nature of work and heat.